The title of my project is The Monty Hall Problem, to Switch or Not to Switch. My name is Sabrina Washington, and my advisor is Dr. Lisa Galminas. For my project, I based it upon the 70s game show Let's Make a Deal. And in the game, the host, Monty Hall, would present a contestant with 3 doors. Behind one of the doors was some grand prize, and behind the other 2 doors were lesser prizes or booby prizes. For the sake of my project, I will make the grand prize a brand new car, and I will make the lesser prize goats. So in the game, he would present a contestant with 3 doors. He would then tell the contestant to choose a door. Once they choose a door, Monty would always open one of the non-chosen goat doors. He would then give the contestant the option of sticking with the original door they had chosen or switching to the other unopened door. So of course the contestant wants this car very, very badly, so the ultimate question is to switch or not to switch. This Monty Hall problem has been very debated, a much debated math problem over the years. And I like to call it the 2 sides of the argument, the sticker versus the switcher. And one thing that the stickers say is that once Monty eliminates one of the non-chosen goat doors, that they have a 50-50 chance of winning the car. So in order to avoid buyer's remorse, they might as well stick with the door that they originally chose. To approach my project, I began by actually playing the game myself. I played it online, and 100 times I stuck with the original door I had chosen, and the other 100 times I decided to switch. And my results, I won 30 out of 100 times when I was able to stick with my door, and I won 56 times when I switched. So I almost doubled my chances of winning by switching doors. Okay, so supposing you choose the stick strategy. If you select the card to begin with, you will always win, which is common sense. You choose the right door, you're sticking, so that's what you finish with. And you'll win 1/3 of the time by doing that. If you select the goat door to begin with, of course, that means you will always lose, so you're losing 2/3 of the time. Alright, so supposing you choose the switch strategy, if you choose the door with the car behind it to begin with, this means that you will always lose because you're switching from the correct door to a wrong door. And this happens 1/3 of the time. And if you select a goat door to begin with, you will always win. And this is because if you select the goat to begin with, Monty's going to automatically reveal the other goat. So the only thing you have left to switch to is a car. And this happens 2/3 of the time. So you are able to see that in playing a 3-door game under these rules and conditions, it's always in your best interest to switch doors. Next, I looked at a game in which we kept the number of cars at 1, but we increased the number of doors, which means that we also increased the number of goat doors. So I looked at a 4-door case in which we had 3 goat doors and 1 car door. And the same rules applied that Monty always revealed a non-chosen goat door. Alright, so sticking. Your probability of winning by sticking was your probability of choosing the car door to begin with, which was 1 out of 4, or 25%. And your probability of switching was your probability of choosing the goat door first, times the probability of switching to a car door, being that you chose the goat door to begin with. So your chances of choosing a goat door to begin with are 3 out of 4. And if you choose a goat, Monty's going to eliminate the other goat, so then you have a 1/2 chance of then choosing the car. So 3/4 times 1/2 is 3/8, so you can see that 37.5% is greater than 25%. So once again, you should switch doors. So then I generalized this. I kept the number of cars at 1, and I made it n number of doors. So this means that we have n-1 goat doors. Once again, the same rules apply, where Monty always opens one of the non-chosen goat doors. So your probability of winning by sticking is your probability of choosing a door with the car behind it to begin with, which was 1 out of n. And your probability of winning by switching was your probability of winning by choosing a goat door first, times the probability of choosing a car, being that you chose a goat door to begin with. So I'll use your pointer. Here, in order to choose a goat door first was n-1 out of n doors, times your probability of switching to a car. You have 1 car, and if you started with n doors, you chose a door, he eliminates the door, so that's n-2 doors. So what I did, I manipulated this to look like this, so that it was easier to compare to sticking. And we know that n-1 over n-2 is some positive number greater than 1. And you can see here because the numerator will always be greater than the denominator. So if 1 point something times 1 over n, of course, is greater than 1 over n. So you can see that you should switch doors. And what I did, I made a summary of my observations where I let the number of doors be 3, 4, 5, 6, and 10, and also I showed indoors. And I kept the number of cars constant, and you can see in each case that as the number of doors increase, your probability of winning by sticking decreased, and also your probability of winning by switching decreased. And at the same time though, in each case, your probability of winning by switching was greater than that of sticking. But as we increase the number of doors, I let the delta up there, I let that equal the difference between your probability of winning by switching minus the probability of winning by sticking. And you can see that as the number of doors increased, that difference became smaller and smaller, and you can see that it'll approach 0. So then, same rules, new game. We can generalize further by increasing the number of cars to some fixed m. It can be 2 cars, 3 cars, 5, 10. And observing the relevant possibilities for the varying n values, where n was the number of doors. Alright, so we must assume that there are always at least 2 goat doors in play. This way, if a contestant chooses a goat door to begin with, Monty always has another goat door in the game so that he can reveal it to abide by his rules. So I looked at a case in which there were 2 cars and 2 goats. So your probability of winning by sticking was your probability of choosing a car door to begin with, which was 2 out of 4, which equals 1/2. And here, you can win by switching 2 ways. You can win by picking a goat door first and switching to a car door, or you can win by choosing a car door first and switching to the other car door. So you have a 1/2 chance of choosing a goat door to begin with, times, like I said, if you choose a door, he reveals a door. If you choose a goat door, he reveals a goat door. So the only thing left to switch to is a car. That's why I have times 1. Plus your probability of choosing a car door first, which is 1/2. And if you choose a car, he eliminates the goat, so then you have a 1/2 chance of switching to the other car. So 3/4 is greater than 1/2, so once again we should switch doors. And I made a generalization of my observations. I let n be the number of doors, m be the number of cars, and n minus m equal the number of goats, with n minus m being greater than or equal to 2. So what I did, I had the cars, 1 car, 2 cars, 3, 10, and m. And you can see that it followed the same pattern like it did for the other case, where this would still be a positive 1 point something, the n minus 1 over n minus 2. So times that would still be greater than what you have for your probability of winning by sticking. So you can see that in any case, no matter the number of cars, your best chances of winning are by switching. Same game, 2 players. So now let's assume that 2 players are playing a 3-door game in which there is 1 car and 2 goats. Alright, so things to keep in mind. Neither player will know what door the other player has chosen. Monty will always open a goat door, if possible, in front of both players. If Monty is forced to open a car door, then the game would just be over and both players would go home with goats. And if both players choose the same door, they'll just simply get that prize. Alright, so ways that the 2 players can initially choose their doors. Both players can choose the same car door, of course. Each player can choose a different goat door. Each player can choose the same goat door, or 1 player can choose a car door and 1 can choose a goat door. So what I did, I actually wrote the ways in which player 1 and player 2 could choose their doors. And as you can see, I put strike-through marks between 2 of them, and that's because if each player chooses a different goat door to begin with, Monty doesn't have another goat door to reveal. So there are actually 7 ways in which the players can choose their doors in order for the game to continue. So you can see here that your probability of winning by sticking would be your probability of starting with the car first, which is 3 out of those 7 times. So you win 3 out of 7 times by sticking. And your probability of winning by switching would be 4 out of 7, because if you choose a goat, because you see there's 4 goats left, and if you choose a goat door, he'd automatically get rid of the other goat door, so you're always switching to that car door. So you'll win 4/7 of the time by switching, 3/7 of the time by sticking, so you should switch doors. So then I looked at a case in which there were 2 cars and 2 goats in play to see would I get the same results. And because there are 4 different options now, we have car 1, car 2, goat 1, and goat 2. There are 4 ways in which each player can choose these doors, so 4 times 4 is 16. There are 16 ways in which the players can choose their doors. But we must take into consideration the times in which the players would choose the same goat door. the different goat doors, so Monty wouldn't have one to reveal. And that happens twice, so there are actually 14 ways in which the players can choose these doors in order for the game to continue. So in order to find the probability of winning by sticking, I knew that there were 2 ways in which player 1 could choose a card to begin with, and 4 ways in which player 2 can choose the rest of the doors. So there were 8 out of 14 was your probability of winning by sticking. And for switching, once again, you have to think about it as you can win by starting with the goat door to begin with and switching to a car, or starting with the car door first and switching to a goat door. And I found that to be 10 out of 14, which was 71%, so you should switch doors. So this time, I kept the number of goats constant and I increased the number of cars to see what would happen. And I saw that if we increased the number of cars, P-stick and P-switch, those probabilities both increase, but at the same time, P-switch is still greater than P-stick. And that difference between the two as we increase the number of doors are once again getting smaller. Same game, more goats. I performed calculations for multiplayer games in which the number of contestants equaled the number of goats and kept the number of cars constant. Alright, so this is what I got. I fixed the cars at 2, and like I said, I had the number of contestants and the number of goats the same. So my results followed just like the original game, where my probability of winning by sticking decreased, and my probability of switching decreased as the number of doors increased. And also, the difference between the two, that decreased and approached 0 as we increased the number of doors. And I also looked at a 3-car case. I kept it constant at 3. Same thing happened. They both decreased. P-switch was still greater than P-stick, and the difference between the two approached 0 as the number of doors increased. And the last thing that I did was try to look for a general formula for P-stick and P-switch. So I let M be the number of cars, N be the number of doors, and N minus M equals the number of goats, which equals the number of contestants. And I came up with these formulas for like the viable outcomes, the number of outcomes beginning with C, which is the car door, and the number of outcomes beginning with G first. And I got all of this, and I won't go into detail about it, but if I were able to continue working on my project, one thing that I would do is try to prove why this is greater than this. And also, if I had more time in my project, I would look for other scenarios in which we could find a way that P-stick would be greater than P-switch, because I didn't find one this semester. So what I've learned, throughout this project, I observed that whether we keep the number of car doors constant and increase the number of goats, or keep the number of goats constant and increase the number of cars, is always in the best the contestant always has the highest probability of winning by switching doors. And that's it. That's my work cited.
We have time for just a couple of questions. Anybody has questions?
Do any of you have questions?
Is the door locked?
Yeah.
No, the doors are not locked. You have to open them to reveal the car.
And there comes a car.
Okay, thank you, Sabrina.